You're listening to Engineuity, the podcast that dives into the wonderful world of everything industrial. From the birth of the first combustion engine to breakthrough hybrid power technologies, Engineuity examines just about everything the industry has to offer. The podcast provides a platform for industry leaders, engineers, scientists, and small business owners to educate listeners about past, present, and future industries across the planet.
Okay, well, welcome to episode 4 of Engineuity. I'm Zach Turner with Anderson Industrial Engines and delighted today to be joined by Mike Terzo, CEO of Terzo Power Systems. Mike, can you start out just by giving us a quick background, personal history, education, and maybe like the elevator pitch on Terzo Power Systems?
Yeah, no, thanks, Zach, for having me on here. Yeah, I can give you the elevator pitch. It's a pretty long elevator pitch usually, just because it's really hard to describe what we do, especially to people outside of fluid power or outside of the industrial market. So, but really what we do is we just try to electrify fluid power. That's the short elevator pitch. It gets definitely more complex the more we get into different sectors and different applications. But we electrify fluid power with our primary product, which is the Hydropulse, which is really a smart hydraulic pump. So yeah, that's the elevator pitch, and we can dive into the details at any point.
Yeah, we'll definitely get into the weeds a little bit today, hopefully. You're an engineer by background, by trade?
Yeah, I'm a mechanical engineer and civil engineer, and I've done both civil and mechanical for a long time, but really have been doing exclusively mechanical for the last probably 15, 16 years. But nowadays I don't do much engineering. So.
Yeah, I mean, busy, running a business and all that, right?
Yeah.
But that's kind of the first topic I wanted to get into, which was the entrepreneurship side of where you're at and what you're doing. There's a certain class of engineers that make good business people, and there's definitely a class of engineers that do not make good business people. But I know that you worked in the industry before starting Terzo Power Systems. But what was the spark for you to go off and start your own business in this sector? Like what drove you there?
I think being an entrepreneur is just built into certain people, so I think you have to have that to begin with. If you don't have that, natural innate desire to, want to wake up every day and develop something, then I think it's pretty tough to start without that particular, it's just something innate in all of us. So I think that's driven me my whole life. And I think when I got into the fluid power market as a applications engineer for an integrator, that's really when I started seeing that there was some huge gaps in the technology roadmap in my mind of what had to be done for fluid power to really get a lot of different sectors to the next level is in terms of electrification, hybridization, digitization. What we call it a lot of different things, but working in the industry really and having that entrepreneurial, spark inside me, those two things just combined to really push me to create this company. I had started other companies before, so I had I had done it several times, both successfully and unsuccessfully, and you sort of learn each time you go what mistakes not to make, and then you end up making a whole new set of mistakes on the next round. So,
well, as long as you're learning every time, I think you're doing it right then, huh?
Yeah, eventually maybe we'll run out of mistakes to make, but I doubt it.
I doubt it too. So it occurs to me that in our industry, there's a reasonable amount of entrepreneurship in the kind of off-highway industrial industry. But from what I see, that's mostly people that come up with an idea for a whole new machine or a solution to a problem that ends up being, a complete piece of equipment, as opposed to someone coming in and saying, hey, I have a different way to do this from a component level. There is some of that, but not not that much with hydraulics. There's from my perspective, there's not a lot of people that decide to step up and say, listen, here's a whole new option to replace hydraulics. Now you have the main industry players coming up with new products and new types of hydraulic pumps and systems all the time, but I think you're pretty unique in trying to, I don't know if I want to say disrupt, but trying to evolve that fluid power industry from a component level, right?
Yeah, and we'll talk about the component versus system hopefully a little later in this, but yeah, it's interesting. I didn't realize that there was almost no other companies that are really starting from scratch to look at what needs to be done in fluid power. Almost everything out there is an incremental, small step change pushed out from the larger manufacturers. And they do that within, a completely different mindset. Obviously big corporations, they don't innovate as well. They have a challenge seeing, the customer perspective, and, combine that with that we just have it. It's really difficult to develop something in this industry, and it's been probably historically almost impossible. But until a lot of different things coincided with the technologies on electrical circuits, on power electronics, on permanent magnet motors, the access to a lot of those different pieces of technology allowed us to do what we're doing right now. But yeah, there is there is not a lot of innovation going on other than trying to improve the existing product, very incrementally.
Right. Looking for efficiencies or small additional features, or maybe just some, easier integration, easier use type stuff seems to be most of what changes in that industry.
And it's because it's a system component driven industry. So when we look at fluid power, nobody really looks at it as one supplier is making the whole system. Everything I did as an integration or an applications integration engineer was you take a whole bunch of different pieces from a lot of different manufacturers and you put them together completely differently every single time.
Yeah.
And that flexibility, was driven off of the wide array of applications we see, the wide, different sectors, on highway, off highway, all these different applications. So you have to take different types of components, put them together for the system, and allow the OEM to do what they're doing. But that's now something that we approach very differently on how we do it. We actually can call the Hydropulse a complete system. It can be a complete system, but it can also be a component of a subsystem.
Mm-hmm.
So
Did you start Terzo with Hydropulse in your head? I mean, did you have the product idea for what it could be, and then you went to start the company to build that product, or is it an evolution?
No, it is. I started it with the singular goal of developing the Hydropulse. I had exactly what I wanted to develop based on a lot of the pain points I had seen, a lot of the technology I had been exposed to or done product development in prior jobs and consulting work, and I had put a lot of different pieces together before I started this company. Put those pieces together in my head and said, this is what needs to be created in order to enable fluid power to move to the a fully digital experience, I guess, in some form or format. But yeah, I knew exactly what we wanted to create, and I didn't quite understand how long it was going to take to create that.
Well, that was going to be my next question, which was, from the time you mentally committed yourself to starting the company to build the product in your head, how long did it take you before? I know you are recently into kind of mass production. What was that roadmap for you? How long did that take?
I would say the genesis easily goes back almost 15 years when I was doing a lot of work in electromechanical hydraulic replacement. I think a natural evolution of engineers when they work with fluid power is to initially take the approach of let's get rid of hydraulics and go all electric.
Yeah.
Because there's a lot of precedent for that in industrial applications with servo drives and servo motors and CNC machines and all that kind of stuff. And that's sort of where I started. I was like, let's get rid of all this, messy, oily, loud hydraulics, and let's develop something that is all electric. And being an entrepreneur, I actually, tried to develop quite a few different alternatives a long time ago. I think that was probably at least 15 years ago. And then when you do that, you start realizing, the realities of physics. You learn the realities of, and the limitations of electromechanical, and you really start learning the benefits and power of fluid power. And that started leading me to combine those thought processes and look at what is the best solution for motion, not just like what's the best solution for hydraulics or whatever, but at the end of the day, the only thing we do is we try to affect motion on a machine, linear or rotary. That's it. That's all we do on the planet. Every machine boils down to either a linear motion or a rotary motion. So I spent quite a bit of time looking at how can we combine the best of both worlds, because there is the significant advantages of hydraulics and significant advantages of electric drives and electromechanical. And that was really the genesis. But that went back, well over a decade ago, before I really worked through quite a few years of just, in the background of my brain, looking, trying to figure out the best product solution. Because it's actually an iterative process in my brain, because you have to think of all of the outcomes before you start a company. You can't start. You can't be a product looking for a customer. You have to know the pain points deeply, and know. You might not know all the challenges to put all that together, but you have to know the pain point. And I think before I was a fluid power applications engineer, I understood a lot of the technology, but then going into the integration side and the application side, that really taught me the pain points. So I could put those two together and take the technology and the pain point and create the correct solution. So
yeah, we've had some experience with OEMs that decide to take a hydraulically driven machine and just, let's go all electric with it, get rid of the hydraulics, get rid of the engine, go all electric, and almost always underestimate the amount of work and the difficulty and a lot of the nuances and controls issues that you have going, from hydraulic cylinders to linear actuators and hydraulic motors to electric motors. And it really underscored for me how the and we'll get into what Hydropulse is here in more detail, but how that offers almost a bridge to get people to all the benefits of electronic control without losing any of the downsides of fluid power, right?
That is, you summed it up correctly. We allow you to do fluid power, hydraulic motion, the way you do like servo drives and electric motion. We talk the same language. You can control it with the same thought process, the same controllers. So that is it is truly a bridge in that respect.
Well, so let's dive into Hydropulse a little bit then. So, for the uninitiated, can you give us the basic overview of what a Hydropulse? Let's talk about as a unit for right now, or as a component right now. What is a Hydropulse motor?
Yeah, and it's been sort of a changing term as far as what we make, because there's not really a good, is it a hydraulic power unit, is it a smart pump, is it a pump, is it a motor, is it a pump motor unit? That's why we just call it a Hydropulse. But in essence, it is everything combined. So we take a motor, a permanent magnet motor. We combine it with the pumping means, which is typically we prefer a gear pump. It's simple, it's robust, and cost effective. And then we put the motor controls. We embed the motor controls in the form of a inverter, and then we add the electronics on top of that. And all of that from the electronics, which really controls, which is the motor controller. You know, depending on what industry you're in, it can be called an inverter, a drive, a servo drive. You know, it's a lot of the similar things of a VFD. It's all just slightly different ways to control a motor. But the motor controller, electronics, motor, and pump. So it's really those three things, but the combination, when you start integrating those things together in a very compact, tight package, you start running into all the issues that we've had to deal with for, you know, almost a decade of solving all those problems. Because anybody can bolt those things together. You know, there's a lot, the industry has been bolting these things together for almost 30 years, I think, maybe even more, especially like servo motors bolted to pumps. Mm-hmm. Injection molding machines have been using that for several decades. So it's a well-known outcome, but when you try to bring all those things together for the particular application, and I chose the most rugged application first, because if we can make it work in the rugged off-highway market, it's going to be a piece of cake to apply that into industrial applications.
Yep.
But you still have to do it cost effectively in industrial applications. So, we've combined all those things, integrated them together. They work seamlessly. You have to take thermal considerations in, cooling. There's a lot of electromechanical issues where when you're embedding electronics into a mechanical housing, there's a lot of stuff you have to consider and work through. We've had to really develop a lot of pieces from scratch in-house that I never pictured we would do. We now are complete power electronics experts. We've had to develop all that. You can't go ask somebody or hire somebody to do a power electronics system for this, because nobody's really done it before. So we had to learn a lot of that in-house, and that's been a long road, but it's been pretty fun.
Yeah. There's as you say, it's a lot more difficult than just bolting stuff together, right? You have to really integrate those components into a system that works together. As we get deeper into this Hydropulse conversation, you're going to realize that I only know the very basics of hydraulics and fluid power. I'm an electrical engineer by trade, so you're going to have to help me through some of the hydraulic parts of this discussion. But for selfish purposes, I want to start off talking about the motor. So you're using a 3-phase AC permanent magnet motor drive, right?
Correct.
But you've got the feed of the Hydropulse is a 48 volt DC power to the motor?
We actually created a very one of the powerful things that we did, and I think one of the things that is already proving to be very successful is we spent a long time, because I think you could go and you could develop something like this in a lot shorter amount of time than it took us, but you would not have developed the architecture that allows us to scale into so many different applications. And voltage input is a really good example, and the motor. We've created the architecture that allows us to go after a lot of different voltage inputs, a wide range of inputs. So we've sort of boiled it down into low voltage and high voltage, which is sort of up to 48 volts, and then from over 48 up to about 800. But inside our electronic architecture, almost everything is identical that allows us to do that. There is a couple key pieces of difference, but we don't have to redesign and revalidate and retest almost everything when we have different versions. So it's like everything else, the setup takes most of the time, and developing that scalable architecture that is completely hidden behind the scenes and underneath the hood there took a lot of time, because you have to, you can if you're going to do a low voltage motor controller, you can get away with a lot of certain things, and if you're going to do a high voltage motor controller, you can get away with other things. when you're trying to do a scalable architecture, you can't really cut corners on so many different aspects, and that creates a lot of challenges that we had to overcome, and it took a long time.
So customer can bring their own range of different power inputs to the Hydropulse. You guys are doing the power handling or inverting it as necessary to get what you need for the permanent magnet motor that's driving the Hydropulse. Why a permanent magnet AC motor instead of something like a servo? Like you mentioned, there's already a lot of reasonably high torque, but also high precision applications out there for servos and other industrial spaces. But why was the choice of AC permanent magnet important?
Well, it is a servo motor, so the motor topology is pretty much the same that's in a servo motor, and it actually you can consider our product inside it is a servo motor. We have a full absolute encoder on the motor feedback, so
it knows its absolute position at any given time. Then
yes,
okay,
yeah. So it is a servo motor. It can perform the same coordinated motion functionality. If you're putting it into coordinated motion applications, which we will be doing, we needed a lot of that functionality. But specifically we chose, which is something that's still confusing, I think, to everybody, is especially people that are not motor people. A lot of the terminology is confusing with PMAC, permanent magnet motor, servo motors, brushless DC. There's so many terms out there, but what we use is an interior permanent magnet motor, which takes an AC waveform, and that's the actual motor core. But you can send in AC or DC depending on what configuration we have, and then we're doing either the rectification and inverting, or we'll do just the inverting to control the motor.
Okay. Moving on to the hydraulic side then. So are all the Hydropulses, I know you have different application specific pumps, but the general purpose Hydropulse, are those all gear pumps on the hydraulic side?
Yeah, we did. We just launched a sort of an SAE, spline shaft pump mount, where you can mount whatever pump you want.
Oh.
So it's sort of pump agnostic, and that's primarily for a lot of people to test a lot of different pumps quickly for their particular platform, and then some of that could, or if there are some applications where it makes sense to use a piston pump if you're going after really high pressure outputs. So there's some outliers, but the vast majority, I would say probably 95% plus, is all external gear pumps.
Okay. So in that case, thinking about a machine architecture, is the idea to have, well, you can probably do it both ways. You have a Hydropulse for each machine function, and a dedicated motor, dedicated control for each machine function. Or do you still envision people using maybe one prime mover Hydropulse and then using like a valve body, and traditional hydraulic valving to control individual functions? Or can you do both?
You can do both, any and all of the above, and that's really what I found is one of the biggest challenges with introducing anything that's outside of the normal system architecture, is having people understand how to apply it. And what you just mentioned is actually hard for a lot of different folks to understand, that you can run it however you want. It totally depends on the application and what you're trying to achieve, which would dictate sort of how you're going to apply it. I think a lot of experts in hydraulics would all agree sort of that we've came to the conclusion that if you can remove every valve from the system, you're going to be the most energy efficient system you can possibly achieve with hydraulics. But then you have to add on to that, the cost of that system, because we could have done that a long time ago. It would have just been very, very cost prohibitive, and way too complex. But that is an architecture that we push. We don't really talk about that a lot because I think it's to a lot of people, they're not quite there on that architecture of saying like, oh, we're going to put one Hydropulse on every single work function. But we're starting to see that broader acceptance of different architectures because we have different market drivers in the industry right now. We have such high pressure on different sectors like the on-road heavy trucking. Now the off-highway is really being pushed to work on energy efficiency, and there's a lot of stuff going on that is broadening the acceptance of looking at different architectures, and that was not the case even 5 years ago. I mean,
I think that's changing really, really rapidly in the industry right now, and a lot of the engineering effort we're seeing too is just efficiencies. There's a lot of incentives around finding a more efficient system, even if it's only 2, 3, 4% more efficient. If that gets you into a smaller engine, a smaller carbon footprint, and really just optimize around efficiency, whereas even 10 years ago, it was people didn't have any problem just throwing horsepower at a problem, right? And that's changed a lot.
Yeah, it's changed a lot. And, when I started a long time ago, I started by looking at how do I make a hydraulic system more energy efficient. And that really led me to some of the, ideas and thought processes around a distributed pump system. Because at its heart, if you can't remove the valves, there's no way that I could come up with that you could really improve energy efficiency very much. You could always do little, teeny little tweaks to the system, but you would not really be able to affect any kind of even on the order of 5% improvements. And, which is what the industry's been doing for the last several decades, is really trying to just squeak out those last couple of percentage points of efficiency by getting ever more complicated valving and pump control means. But that has also created ever more complex systems that is still doing the exact same thing. So I just looked at that and changed it and said, how we're still doing the same thing. Can we do it simpler and more energy efficient? The energy efficiency is easy. I mean, we really, really improve energy efficiency across almost every application, anywhere from, worst case is probably, 10 or 20% improvement, but we've now documented, 96% reduction in energy usage on applications, and that's part of some of the stuff we've published with the California Energy Commission on our grant. But across the board, 50 to 80% should be expected in a lot of applications. It definitely depends on the application. So energy efficiency, we can do a lot with that. The next thing is cost. You have to, no matter what, you have to do it at the cost point that the product, the sector, the market is going to accept. And that's...
And is that in the context of a total cost of ownership? I mean, when you're running a piece of equipment, efficiency is cost, especially if you're burning fuel to run the machine. But are you able to make a total cost of ownership, pitch with the product, or are people... Is there some limit to like their upfront cost sensitivity to... It doesn't matter what the TCO picture looks like, that if it costs more than this, they're never going to buy it?
I think it's both, and I think it depends on the sector and the vehicle and what people are doing with it. If you're buying an excavator, I think there's a more acceptance of TCO conversation because they're used to that. They're used to buying that type of equipment on a TCO business case. If you're talking about an industrial power unit in your factory, that's a lot harder to sell on either an ROI or a TCO base because typically in that application, the person purchasing the capital equipment, the person with the CapEx budget, is not the person that pays the energy bills.
Yep.
And they know they can get a cheaper hydraulic power unit. And historically, if you were trying to sell a servo-driven, hydraulic power unit that's out there, that's why I started the company, is because I was out there trying to sell what was, provably a significantly higher performance system in terms of energy, performance, noise, weight, everything with a bolt together. But you cannot sell that because of that. We had the ROI under a year, and we could not sell that type of system to factories just because of that disconnect. So that's what I set out to do, is like I knew if I went in with that solution at the same cost point, then you're talking about completely scalable solution, because then you're not arguing on upfront cost, and
Yep.
you're not going in with a sales pitch of like, yeah, it's more expensive, but here's all the benefits. You have to be talking to the right person to have that conversation.
Right.
If you're talking to the person that has a budget and that's all he can work within, it's going to be a tougher conversation to say, oh, what, after a year, you're going to be saving money, and you're going to be, so it was really a challenge. So we looked at cost parity. I look at everything from a cost parity perspective. Whatever we introduce, you have to be able to get to, on par with the conventional product you're displacing in terms of cost, or else, I always put that into a tougher sales category, and I didn't want to start a company that were always trying to sell on ROI.
Yeah. Well, I was poking on your website. You've got a chart of the, overall efficiency compared to, dollar per kilowatt cost based on a few different platforms, from electric motors to CI engines and stuff. So, are you where you want to be in terms of cost parity to a CI engine or an electric motor, for a plant installation? How close are you to that parity point?
I think we're there, or we've exceeded it. And there's always such a big range because it depends on what's the application. I mean, it's everything we deal with is what is the application and how are we applying our technology, and that's going to dictate how and in what manner you would apply it. And for example, if you're in one application, the best solution might be where you're just using one Hydropulse and it's powering a standard valve bank, like you mentioned earlier, because of the price point. That there's no, you have to be cost parity. And I would say in industrial applications, that's probably the preferred approach, is that you're going to apply it as the sort of the prime pump mover. You're still going to go to a hydraulic valve bank that's doing a bunch of functions in everything except maybe single cylinder press applications or injection molding machines. And then we definitely are an improvement in cost. We're an improvement in all of the other metrics, performance benchmark metrics. But if you're going to be applying it into an excavator, most likely you're going to have to go with a different approach. You're going to have to look at it as a distributed pump system, because it's a completely different value statement on what we're trying to do to electrify a piece of mobile equipment versus stationary. But I think we've met the cost goals in that chart. It just depends on which system you're talking about.
Yeah, what you're comparing it to.
And it's much harder to get the cost point at the lower kilowatt sizes. That's why that range, the smaller the horsepower, the higher the cost per kilowatt, and the tougher it is to compete. As we go up the horsepower chain and get into higher horsepower, it gets a lot easier to compete and exceed the existing, or I guess improve on the existing cost point.
I guess that's counterintuitive to me. I would have thought that you would have an easier time comparing on a dollar per kilowatt basis on smaller applications, because just the amount of stuff you need to make let's say a 25 horsepower 3-cylinder diesel, is a similar amount of stuff, just in a larger size. You need to make 200 horsepower, and the dollar per kilowatt curve, at least on a CI engine, tends to favor larger horsepower.
Yeah, for us, it gets much more competitive. the bigger the unit and the bigger the horsepower requirement. And it's for two reasons. Because one, our internal cost per kilowatt, and most things, it gets lower. So you get more bang for the buck as you go up in motor size.
Right.
So you're a 30 horsepower or 100 horsepower, the cost per kilowatt is a lot lower than 1 kilowatt, because on the electronics, no matter what, you still have sort of the same amount of stuff in there. You'll just have a way smaller, either IGBT or MOSFET on the actual switching devices. But then you go up and you could have a 200 horsepower motor. You're still going to have the exact same all peripheral electronics, and cost per power. Your switching devices don't go up that much. So your ratios really tend to look a lot better as you go up in power. So that's one reason. The other reason is you start really gaining huge efficiency advantages when you go up in horsepower, because those machines get worse and worse as far as oversizing the machine and having a lot of excess power on the table because in a lot of this stuff, we look at the excess power that you have. That is dollars sitting on the table that we get to remove because of the power on demand nature of everything we do. So if you have a 200 horsepower excavator, chances are that we can power that entire excavator with maybe 50 horsepower, 60 horsepower. So if we had to apply the exact same power levels of Hydropulse, then it would be probably a different conversation. But we get to grab so many inefficiencies and throw them out the window and put in such a smaller system to do the exact same performance. That's where we really start shining on electrification, and that's the opportunity that presents itself on bigger and bigger equipment.
Yeah. So what is the current range of Hydropulse, and how do you measure? Do you look at it in terms of a kilowatt sizing, or how do you size them, and what is the current range of sizes you guys are making today?
Yeah, we pretty much just talk in sort of our frame size, which right now we have our F1, F2, and F3, and that's our frame size 1, 2, and 3. We're not very, inventive here in terms of that. So F1, F2, F3. Our F1 goes up to about 3.5 kilowatts. Our F2 goes up to about 10, and our F3 actually is scalable to over 100 kilowatts. And then past that, right now, we would just say take two F3s and put them together, and you get 200 kilowatts. Put three of them together, because you can do very unique things as far as pairing them together to provide, again, depending on the system, because we're totally rewriting how you're approaching a system, because one system might have been, like you said, almost everything is one prime mover, an induction motor or ICE engine. That's it, powering a big pump stack with maybe a belt-driven or gear-driven auxiliary hydraulic gear pump, all kind, But that prime mover is powering the hydraulic system. What we can do is once you take away or decouple that in a hybrid, now we can approach it completely differently, because maybe you go electromechanical on stuff that's less than 2,000 pounds of linear force. Maybe you have like one F2 powering a couple functions over here, and you have one F3 powering a valve bank somewhere else. You can totally look at the system architecture differently to optimize your power for the work functionality. And that's something that we don't get to do when we bolt pumps onto an ICE engine and we bolt pumps onto an induction motor. We have to build the entire system around the torque curve of that engine or that motor. And it's almost in every single system. And I still welcome any application that doesn't oversize their hydraulics and their engine for one use case, right? So you're always, like you said, it's just like, we're not quite getting the speed on one function. Let's just jump to a higher engine or a bigger pump size. Yep. What that does is it actually oversizes your whole system and creates an even worse efficiency chain. because now you're invariably never operating in an optimized power band for your system.
Yep.
You might be for a very specific time, say ground drive on an excavator. That's optimized for flow rate usually, or sometimes for pressure, but usually for flow, so you can move fast. Well, that dictates the sizing of everything else, which chances are now all kinds of stuff is oversized. And that scenario where you're wanting to go really fast up a hill is a pretty rare occurrence in most excavator lifespans or duty cycles. And in that instance, when you decouple that ice engine, we can address that application easily by using peaks. Because peaks we can do up to 2x the output power. So if we say our F2 goes up to 10 kilowatts, you might be able to do 20 kilowatts for a certain duration. So then you can actually size into that peak range, because all our sizing, like our F2 is 10 kilowatts. That's continuous with a given temperature, but that's pretty much continuous. Well, if you're just a little bit over that, you can go close to continuously. If you're at 11 kilowatts, maybe you can go 80 or 90% duty cycle, and then it goes all the way down to where maybe it's only 30 seconds at twice that range. So you can look at that specific worst case function on that vehicle and say, can we utilize that peaking area, and then we don't have to oversize everything else.
Yep.
And that gives you massive flexibility on design of these systems.
Yeah, that's a whole different engineering mindset. I mean, I think there's a lot of people are used to dealing with a fixed amount of output power from an IC engine and just don't think about the possibilities when you start freeing up that additional kind of boost or peak power. It's just a different mindset. It's just not something that's been on the table before. So it's very interesting.
Mindset is everything, I think, with electrification of fluid power. Everything requires throwing a lot of what we've learned for 100 years out the window. Hydraulics has been around, I think, for thousands of years since, but we have to throw everything we've thought of as, how to design a system. You throw it out the window and you start from scratch. And that's the way we approach it with OEMs, because typically when we're working with an OEM, we're working on a new platform. We don't do really much retrofit. There's some good applications for retrofit, but typically we're working with them on new development of some type of electrification platform, whether it's a new machine in industrial, or a new vehicle platform, battery electric, fuel cell, hybrid in the off-highway.
Mm-hmm. Well, I want to jump into discussion on some of because you have done some retrofits, and you've done some hybridization projects. What did you engage in those as like technology demonstrators? I know some of those were around some grants and studying other areas of efficiencies and maybe just proof of concept type stuff. But can you tell me a little bit about the work that you guys are doing in hybridization and how that fits in with Hydropulse, or maybe is separate from the Hydropulse business?
It's all related. So I sort of take the approach in our industry is a rising tide lifts all boats. So we have to move the whole industry up. And that industry, actually, who's involved in that industry is getting redefined, because fluid power industry, is becoming much more broad-ranging and broad-reaching than just what it was before. Mm-hmm. But a lot of the work we've done, and most of the work behind the scenes that we do, is to understand the complete ecosystem around electrification of fluid power, so we can best work with the OEMs to not provide just the component that we manufacture, but we want to provide expertise and the help in getting them to their production. That's what it's all about, is helping the OEMs get through their development phase as fast and cost effectively as possible to get them into production to make the vehicle that their customers want. And what I've learned is that because there's such such an unknown on a lot of these pieces. We've became the experts in a lot of the peripherals around even what we do, and we can either point them in the right direction. We can help. We've been which has also led to us launching a high voltage fan, a coolant pump, other things where there's just missing pieces. And the projects we've done have really been to understand that ecosystem, because if we can't tell people how to apply our product, then they're going to have a tough time wanting to buy it. For different, some of them are really easy. It makes a lot of sense. They can wrap their brain around it. Some of them, especially like an off-highway, most of the questions are like, okay, what do I do with this? What do I do with your product? And we've had to understand that system and do a lot of the development. Even if we do some development, because like in the when we did the tree shaker hybridization project, we did a lot of work that we're not going to probably commercialize pieces of those technology. If we get some of that information out and it helps the industry move forward, then that's a win too, because that's going to also drive the growth of our company.
So some of the other products that you have developed along that road, high voltage safety system you mentioned, I know there's some thermal management pieces in there as well. Are those products that you intend to take to market in addition to Hydropulse, or those things that you just built because you had to and won't make it as part of the long-term portfolio?
It was originally the intent that we were going to commercialize those as our own in-house products. What we've learned is if you blink, half a year later, somebody's probably came out with some piece of that component that might not make sense to, because if you're going to commercialize something, you have to do it pretty darn quick to make sure that you're utilizing best in class, sub pieces or whatever. But what we're doing now is we've really learned what we are as a company and what our core competency is. That's, I think, the journey of every entrepreneur and every company. When you start the company, you always envision it as one thing, and you typically, it might end up somewhere else. And while our core product, the Hydropulse, has not changed from day one, it is. Even form factor, the thought process, the sizing, everything is exactly what I envisioned. What is different is our company. I originally thought it's like, we're going to have to manufacture these. We're going to have to, do a lot of stuff. And that has been something that's taken us on different journeys as we went through, because now, that's not our core competency. Once you start learning, what it really takes to ramp up and scale for different industries and manufacturing, you start seeing like, okay, we could, I always feel like, we could probably do anything. We're smart. We can figure it out. But is it worth it, financially? Is it worth it time-wise? And we chose, and we were lucky enough to find a really good contract manufacturing partner that's been doing fluid power components for, I think, 30 or 40 years. And by going with a contract manufacturer for that part of it, that has allowed us to focus on the innovation, the technology, the support of the product. Customer support is huge, and also scaling. Making sure we're supporting a scalable product, because that's something that if you're not ready and you can't support that growth, it's going to be bad for everybody. So we're now we work with a contract manufacturer. I really call it a manufacturing partnership, because it's not just a contract manufacturer. You're not just saying, here's our thing, you make it and sell to us. It is a true partnership, because at every aspect we're collaborating, especially in the last couple of years while we've been going through our commercialization and ramp up for full production. It is they are like part of our company, and we are like part of theirs. So it's a deep relationship that has been a great journey for us. It's also allowed us to find out what our core competency is, which is really on the engineering side, the innovation side, and the commercialization. and it's allowed us to ramp up those parts of the business while we didn't have to divert resources to put it, to do the other side, which has been very successful.
Well, we talked a lot about that with the guests I had in the last episode of the podcast, just about those partnerships and finding some of those like symbiotic business relationships is always really important. And it seems that preparation for and launch to actually building a product is where most people fall down. We see that a lot. We've seen that a lot in just like the electric vehicle market in the last 5 years. The number of people that have, brought a really cool looking prototype to a show and then taken a bunch of pre-orders and just not been able to build anything, there's a pretty long list of those folks. And so I congratulate you on being able to actually bridge that gap and get into some production. It
is really hard, and there's more bodies along the side of the road as we speak in that electrification side, because you see that everywhere, and it's because and when they say an idea is cheap, it's the execution that really costs a lot. It's so true, because everything we've learned in the last 7 years, the easiest part was the idea. I came up with the idea and really put that together relatively quickly in our history. Bringing that to market has been an insanely, and again, we make a pretty small thing, right? We're not making a whole vehicle. These companies that and a whole bunch of money you even usually won't help, because if you don't have the skill set and the understanding and how to scale and manufacture something, it doesn't matter. You can throw a lot of people in the wrong direction really quickly. Yeah. And we see that play out a lot. So we've and we've purposely sort of controlled our growth. Especially this year, which is a pretty interesting year as far as supply chain and all kinds of stuff going on. We're trying to, because we don't want to grow too fast. We're growing fast, but we don't want to outgrow, the ability to support our product, which, is we're always straining right at that edge, which is probably means you have the right resources if you're just almost bursting at the seams, but it's always a fine line as you're growing, because you just going from 0 to 1. If anybody's read that book, that's
Peter Thiel.
0 to 1. It's 0 to 0.1 is the hard part, and then it gets really hard after that. Yeah.
Yeah. Well, I thank you for joining me today, Mike. I greatly appreciate your time. I want to close with two kind of tongue-in-cheek questions here. First is, I want your opinion on engine versus motor, because I've had this debate with a bunch of people. But where's the line for you between what's an engine and what's a motor? And we've crossed that line a couple of times just in this conversation. But you work with both, so which is which?
Oh, which, like the terminology, which is which?
Yeah, taxonomy. What's a motor and what's an engine?
Well, a motor is an electric machine, and an engine is an internal combustion machine.
That's the correct answer. Thank you.
Oh, sweet. I thought you were going to ask me like what sort of what's the future. I mean, you guys obviously do a lot of engine work. Sort of what the future of the engine layout is in electrification, because that's an interesting question too. So
it is an interesting question. I wish we had some more time to get into it, because I could talk about that for days and days. But the other question I had was what's your favorite application? I mean, you've worked with a lot of different machines that do a lot of different things, but what's your kind of go-to interesting application when you're talking to people about some of the stuff that you've been able to work with that most people probably wouldn't know about, or didn't know that machine existed,
Oh, I mean, obviously the tree shaker, everybody, when they see that in our shop, most people don't know what it is. So that's obviously really unique, but there is, so many unique pieces of equipment. There's one piece of equipment that actually goes into, it has a massive arm that goes into I think it's like a burn chamber, and it goes in there and it actually relines the chamber. And if you looked at this machine, it's the size of a bus, but I think it's for big foundries or something. I'm not quite sure, but it goes in and relines the refractory stuff in this big furnace. But if you looked at that, you would have zero knowledge of what that is. Yeah. Even when you know what it is, you don't know what it is. So that's pretty wild. And then I would say a road header is pretty cool. A road header is probably one of the meanest looking pieces of off-highway equipment, and that's what digs tunnels. Not the tunnel boring machines, the big rotating thing, but a road header has those mean looking, toothed, huge drill bit on the end of an arm. Those things are awesome. They got more hydraulics on them than you can imagine, and it's in the most brutal environment on the planet. Underground, hot, wet, damp, and it is just, its whole life is grinding against stone. So if anybody watches this, look up what a road header is. They're awesome machines. So
all right, we might need to put some pictures in the show notes or something for everybody. So
yep.
All right, great.
And absolutely.
All right, thanks, Mike. Appreciate your time again. Take care.
Yeah, thank you.
Thanks for listening to Engineuity. We record and release a new episode every month. Be sure to follow us at Engineuity Podcast on Instagram for updates about future episodes and industry news.